Today I'm going to talk to you about electricity and complex numbers. I selected a topic that was slightly out of my comfort zone because I live in a very low income part of the state, and there's a lot of students that do not go on to a 4-year school. Some go directly into the workforce, and others go to a local community college. So when I introduce things like imaginary numbers, a lot of the things I hear is, I just want to go to M State and I'm going to be an electrician. I'm really not going to need any of this math stuff anyway. And so my objective today is actually to just explain how complex numbers are involved in electrical circuits, to discuss electrical circuits and a few of their components, and then actually give you some simple applications that might spark some interest in those students who are encountering complex numbers for the first time. I do realize that complex numbers and electrical engineering go hand in hand, and we can take this to a whole nother level. I'm just going to mention that today. I really want to get something that can appeal to students that we see in high school. Why are complex numbers used in electrical circuits? An electrical field is actually just produced by moving a wire past a magnet. And to produce large amounts of electricity, generators rotate a magnet within a coil of wires, or as this picture shows, the magnets are on the outside and the coil of copper wire is rotated on the inside of it. And that creates electricity. And since it's created using rotation, cosine and sine are very natural ways of representing electrical current over time. Also, current, voltage, and resistance are not one-dimensional. They contain both frequency and phase shift, so two dimensions can be shown all at once if we use the complex plane. And operating with just sine and cosine tends to lend itself to some very complex computations. So if we use complex numbers, it actually simplifies those immensely. So we talked about how electricity is produced by rotating a magnet with an electrical coil, but it also involves something, or that involves something called magnetic flux, and it's a crucial quantity in creating an electromagnetic force, or basically electricity. And the change in magnetic flux is what actually causes electrical current. And rotating that magnet produces that change in flux. And there's several different variables that are going on there. You've got the number of coils, the radius of the coil, which actually determines the area over which the rotation occurs, the strength of the magnet, and then the speed at which the magnet is rotated. The faster it's rotated, the more electricity is created. And so this is the electromagnetic force equation, where N is the number of rotations, T is the time, and then we've got the flux. And the flux is actually the magnetic strength times the area times the cosine of the direction of the magnetic force in reference to a line that's perpendicular to the area. You can see here, these vectors are representing magnetic force field, and this is that perpendicular line, and here's that angle theta. And the Fourier series can be used in electrical power conversion, and this is more in the realm of electrical engineering, and power conversion allows you to do all kinds of things. I just listed a few here, like it switches DC electricity produced by wind turbines and sometimes solar power into usable AC electricity. It allows for controlling different lights and speed controls of fans. It powers aircrafts. They have to have a different frequency so that they can be lighter in weight. It allows ships to switch from their power grid to a different power grid if they dock in a different country that uses a different power grid. And it gives submarines the ability to store very large amounts of power. And so there's definitely a strong need for electrical engineering. But like I said, I'm going to stick to some pretty basics, and I'm going to use Ohm's law today. This is the fact that current is the ratio of voltage to resistance, and voltage is measured in volts, resistance is measured in ohms, and current is measured in amps. And power is the product of voltage and current. And these give you, this formula actually gives you just the average current. You can use calculus to find instantaneous current or instantaneous power. So it obviously can become much more complex. So let me tell you some of the components of an electrical circuit. These are the ones that we're going to use today in a couple of application problems. One of them is a resistor. It's used to resist the flow of electric current to ensure that whatever's being powered does not burn out. And resistance is measured in ohms, and it's part of that Ohm's law. And you can write it as resistance is voltage divided by current. And all resistors are color coded. So you have like the first digit, the second digit, the third digit, what you multiply by, and then the tolerance. And it's based on the color of the bands on the electrical circuit. Then there's also a capacitor, and a capacitor stores an electrical charge in the form of an electrical field. It holds less charge than a battery, but it can release it very quickly. And the purpose of a capacitor is just to help smooth out any interruptions in your supply of current. It kind of acts as a storage tank, and it can release electrons when the current is interrupted. So if you have, say, water filling a huge tank, and you've got a spigot that's open at the bottom of the tank and a spigot at the top that's filling it, you can turn on and off that spigot at the top that's filling the pool as long as the pool's water doesn't get too low. So that's your storage tank for the water, and you have a constant flow coming out of the bottom of the tank. A capacitor kind of works that same way. So it's kind of a storage tank that stores up an electrical charge so that if there's an interruption in the current, it can release some of those electrons very quickly and keep that current stable. So current and voltage are actually represented with sine and cosine waves, and sometimes these fall out of sync if there's an interruption, and perhaps you need more voltage than the current that's being supplied. So the capacitor allows that steady flow of current, and it makes up for any loss of current so it can catch up with the voltage. Another component is an inductor, and there's a lot of similarities between a capacitor and an inductor. This temporarily stores an electrical charge in a circuit, and it also helps to keep things steady. It helps to resist changes in current, but it stores the energy not in like an electrical, let's go back here and see, it stores an electrical charge in the form of an electrical field. An inductor actually stores it in the form of a magnetic field, and it's used at lower frequencies than capacitors, and some can be actually used to filter out some frequencies. So here is how you can represent these components in an electrical circuit. So this represents a capacitor. This is my battery here. Here is the resistor, and this is an inductor. And here, the capacitor has a negative imaginary number. The resistor is represented by a real number. An inductor is a positive imaginary numbers. And the letter J is used when you're dealing with electricity instead of I for the imaginary unit, because I can be confused with current. So they use J instead. So here's a couple of examples, and I think that these are ones that you could use with students. I think about our seniors who take STEM math. Students that don't want to take math for college credit, they're the ones that are thinking, you know what, I'm just going to go to a 2-year school. I want to see where you use this in real life. These would be some great problems to use with those students, or even just when you're introducing imaginary numbers, you're going to see that it involves a little bit of trig and some other things. So take a look at the circuit that I've created here. You've got 120 volts of AC current, and I've got a resistor, a capacitor, and an inductor. And I put here that this is represented as a real number, this is a negative imaginary number, and this is a positive imaginary number. So we want to calculate the total impedance and the current. So impedance, I put this on the slide before, and I think I put the wrong word here. It must have auto-corrected, but the impedance from each is measured in ohms. And the impedance is like the overall resistance. And we can represent this in polar form. So right here, I put these three on my imaginary or complex plane. I've got 72J, that is the impedance from the inductor. 45 is the impedance from the resistor, and negative 60J is the impedance from the capacitor. And I've got a note here that the voltage and resistor have the same phase, but the current through an inductor lags by 90 degrees. So there's a phase shift going on. And the current from the capacitor actually leads by 90 degrees. So it's very convenient that these real and imaginary axes meet at 90 degrees, and it just really lends itself well to representing electrical circuits on the complex plane. So first things first, you can see that I added our positive imaginary and negative imaginary numbers. So the 72 and negative 60 became 12. And then I calculated the total impedance. So this is 45 plus J12. And this is just a simple circuit, so you add the impedance together. And I use the Pythagorean theorem and tangent in order to figure out polar form. So the magnitude here is 46.57 ohms, and we've got an angle of 14.93 degrees. So polar form looks a little bit different when you're dealing with electricity. And when you want to find the current, we can apply Ohm's law. And I take the voltage, remember my battery is 120 volts, divided by the total impedance. And when you divide these parts and then subtract the angle. So I've got 2.58 amps and negative 14.93 degrees. So this is the current, and you can see that the current is smaller than the voltage. So it's definitely been impeded. And then this negative 14.93 degrees tells me that the current is a little bit off of the phase of the voltage. They differ by 14.93 degrees. So this is a very simple circuit. Let me show you one more example, and this involves a parallel circuit. So with a parallel circuit, you use a slightly different formula, and Z sub T, this is the total impedance, and this is the impedance in the first circuit. So I added together the 6 ohms plus the 4 ohms, and remember, it's positive imaginary number for an inductor and a real number for a resistor, so it's 6 plus 4J. And then this is the impedance for the other parallel circuit, the second one here, and that is 5 minus 2j. And I'm just going to jump in here. I don't want to confuse you. And I realize that that needs to be a 5. So I use this second form of the formula and multiplied the two complex numbers together and added them. And then I multiplied by the conjugate. So thinking about using this with students when you're introducing imaginary numbers and adding them and multiplying them and such, this takes on a whole lot more meaning if you can show them where it is used. And I have the total impedance here. And once again, I used the Pythagorean theorem and tangent to switch it to polar form. And using Ohm's law, take the voltage, I have a 10-volt battery in this case, divided by the resistance, or that total impedance. And so the current is 1.0889 amps, and it has a slight phase shift once again from the voltage. So hopefully this has shown you a little bit about how imaginary numbers or complex numbers are used in electrical circuits. And you can dive very, very far into this if you are looking at electrical engineering. And hopefully it's given you a tool that you would be comfortable using with students in your classroom.